of y equals a times b to the x, where we would say that if the y-intercept is y when x is 0, so the y-intercept would be 0a. We're going to find some property of what happens when a is positive, negative, a decimal, etc. to the graph. We would say that the parent graph in most cases would be y equals bx. This isn't always true though. There's exceptions to this. Y equals bx, and this happens when to the x when a is equal to 1. So there is an a there, but a is 1, and we just simplify it. And what we're going to do is we're going to make comparisons to a graph in exponential form and to its parent graph to see any differences in repeatable patterns. The first example that they give here is that they have a graph and they have a parent graph. So the graph is y to the 2 raised to the x (3 times 2 raised to the x). In this case, the parent graph would be y equals 2 to the x. And when you make comparisons to the parent graph, again, everything is always based sort of off the y-intercept. If we look at this guy, remember this is my a, so the y-intercept is going to be 0, 3. Here, the y-intercept is 0, 1. And we can sort of base our graph off of that. So they have it here in blue, which is the graph that they're looking at, and then the parent graph is the comparison. And the comparison essentially is it's been sort of stretched. Right, the graph has been stretched from the red to the blue to have the y-intercept at 3. Right. So the thing that we note for this, a is 3, right? So the basic rule of thumb is that if a is greater than 1, then your graph gets stretched vertically. By a factor of a. So meaning, what's the difference between this intercept and this intercept? 1 has been multiplied by 3. So it's been stretched vertically by a multiple, in this case of 3, or by a factor of 3. The other example that they give of that is what happens when a is negative and when a is not bigger than 1. So here we have a graph of y equals negative 1/3 times, this is 3 raised to the x. Its parent graph, we would compare it to is y equals 3x. 3 raised to the x. Because that's my b. That's my b. Y equals 3 to the x. Now, when they make the comparison of the graph, a couple things we know, right? The parent graph is in red, right? The intercept here, again, is 0, 1. Here, the intercept is really different. Here, we have an intercept of, when it's 0, it's going to be negative 1/3. Negative 1/3. So what changed between this intercept to this intercept? Well, 1 got multiplied by 1/3, and 1 got multiplied by negative 1. And look what happened. By multiplying by a negative number, the graph flips vertically across the asymptote, in this case is the x-axis, and it is compressed. And it's compressed by a factor of 1/3, meaning that it's been multiplied by 1/3. So when a is less than 1 and greater than 0, the graph is compressed. And it's compressed by a factor of, in this case, 1/3. Also, when a is negative, uh, uh, it flips across the x-axis, or it flips across its asymptote. I forget how to spell asymptote. I think that's how you spell asymptote. All right. In this case, the asymptote is the x-axis. All right. So or another word for flip you can use is reflect. So they give us a graph here, and they want to know how it compares to its parent function. So let's make that comparison. It was negative 0.5. So the parent function is going to be b to the x, which is 5x to the x. I look here, and I always check everything based off its asymptote, its y-axis. In this case, it's 0, 1. So based off of what we said, it's being raised to the negative, being multiplied by negative 1/2. So it's going to reflect or flip across the x-axis, its asymptote, and it's going to be compressed by a factor of 1/2. So this one is going to be multiplied by 1/2, and it's going to be multiplied by a negative number. So when I do that, that's exactly what I get. It gets flipped. And that's across the board. Every number here along this curve is being multiplied by negative 1/2. So maybe another main number, y'all. 0.85. 0.85. Alright, everything is being multiplied by negative 1/2 in Ry. So let's see, that'd be way up here. Way up here. So if I see a 0 point, whatever, it would be in the 4s, right? Up here somewhere. And then multiply it. 8.5. Around that line. Okay. We can also talk about horizontal shifts. Um, and this happens up here in the exponent component. Um, x minus h. Uh, if it's x minus h, then it shifts to the right by h. If it's x plus h, it shifts to the left by h. All right, and then we also have vertical shifts up and down the y-axis. So this is left and right to the y-axis, and this is up and down to the y-axis. So if k is positive, then it shifts up by k amount, and if it's negative, it shifts down by k. And when it shifts down, that means that the asymptote moves. So when we talk about asymptote, the horizontal asymptote, which is at the x-axis, right? Actually, let me put that. All right, the asymptote is at y equals 0, right? The x-axis. If we have a plus k, the asymptote moves to y equals positive k. That's our new asymptote. And if it's minus k, it's going to be y minus k. So the asymptote shifts up, the asymptote shifts down. All right, so here we have a situation where we have y to the 2x minus 4. So everything gets added by 4 and shifts to the right by 4 units. That includes the y-intercept. So the y-intercept would be here at 0, 1, and now we put in 4 there, and it's going to be shifted over here to 0, 4. Shifts, or 4, 4, 1. First it was 0, 1, so we add 4 to the x, so now it's 4, 1. Everything slides over. When we talk about where it crosses the y-axis here, that gets shifted as well. So remember, that's when x is 0. So when we try to find the y-intercept, it's going to be 0 minus 4, which is 2 to the negative 4. which is 1 over 2 to the 4, which is 1 over 16. So your new y-intercept is 0, 1 over 16. So just keep that in mind too. Okay. Here they have y equals 20 to the 1/2 times 1/2 to the x plus 10. So our parent function would be, since it's being added by 10, we'll just keep it at 20 times 1/2, which would be here in blue, where the y-intercept would be here. What's happening is, since we're adding 10, everything gets shifted up by 10. So this 20 will be added by 10, that'll be 30. Everything in the y is being added by 10 at the same spot. Up, up, up. Okay. So, how does those guys compare? So our first guy we have is 4x plus 2. So since it's plus 2, it's going to shift to the left, horizontally to the left across the x-axis. So here's our parent function here at 0, 1. And then we shift it over by 2, so we just subtract 2 over here, and we get negative 2, 1. Right, we're going 2 to the left on the x side. And over here, we're adding 5, so everything's going to vertically go up by 5. The parent function is over here. Say increasing function, or decreasing, it's a decay because it's going this way. The y-intercept is going to be 0 and 5. And then we put the parent function in. Everything shifts up by 5. Right? And it shifts way up here. So if this is 0, 5, we add 5 to it. And it should be 0, 10. And so everything gets shifted up by 5. Everything gets shifted up by 5. 1.97, 3.2, 1.97, and it gets shifted up by 5. Everything gets shifted up by 5. Alright, so things to note, just like we said before, if it's greater than 1, then it stretches up by a factor of whatever that number is, a. If it's a is between 0 and 1, it shrinks by that factor. If a is negative, it reflects across the x-axis. If h is positive, it's going to shift to the left. If h is negative or minus h, it's going to shift to the right by h. If k is positive, it's going to go up by k. If k is negative, it's going to go down by k. Okay. Alright, so this last section deals with the concept of E. And E is it's sort of like pi in that it's an irrational number. And it's sort of a base number that talks about growth, and sort of a baseline for how fast something can grow instantaneously. And so, and when I sort of think about E, I think sort of about, I don't know, money. Let's talk about a standard equation. Y equals 1, a growth equation, plus 1 over x. Actually, think of it sort of this way. Let's say I have $1. I'll write it as a circle. And let's say I over 1 year or 1 day, double it. I double it. My thing grew by a factor of 100%, right? Because now I had 1, and now I have 2. I doubled it. I have another thing that's the same. That gives me 100%. And let's say the next day I double that. So now instead of 2, I have 4. And then the next day, I double that. Right. This sort of follows along a pattern, a curve. And it is this curve that if we sort of measured instantaneously at the slope or the area underneath or what have you, gives me a particular number, and it caps. There's only a certain a number that it can be. When I think about that problem we just did, it's about doubling. If I had $1 and I doubled it, right? Then I get $2. Okay. If I had, and so on and so forth. So what happened is I replaced that 1 with a 1, right? And I replaced that x over here with a 1. And that's where this function comes from. And then I get 2. Yay, I get 2. So what if I was to have something for, and I kept doubling it and stuff over time at this rate? What if I did it for every month? There's 12 months out of the year. If I was to do that math, well, the money that I have now would be 2.6130. So if I was to, instead of just waiting 1 year to double it, and I doubled it every month, I get more money. What if I did it every day? What if I was to double my money every day? 1 plus 1 over 300 is 365 days out of the year. Well, what happened to my money now? Well, I get 2.6923. Right? I'm getting a little bit bigger, but notice that I'm not getting exponentially bigger, right? It went from 2 to 2.6. I'm still at the 2.6 when I double my money every day. Or do interest every day. What if I did it at every, let's see, 365 days, every hour? So that would be 1 plus 1 over, there's 365 days out of the year, times 24 hours in a day. What would I get? I would get 2.71813. All right. Still getting to a particular number. Well, what if I was to do it every, see, 24 hours in a day, 60 minutes in an hour? So what if I were to do it every minute? So this would be y equals 1 plus 1 over 365 times 24 hours in a day times 60 minutes in an hour. Well, what would I get then? get oh, I made a boo-boo somewhere. 365 times 60 I would get 2.71828. And if I was to increasingly get bigger, so I get a number approaching infinity. Not remember, infinity is not a real thing; it's a concept. But if I was to get really big, I would approach some type of limit, some type of asymptote, and that asymptote would be 2.7182816. I forget. It's an irrational number, just like pi. It's going to go on forever, and this irrational number we call it e. 2.718 is usually the number it goes to. 2.718. And it's in concept it's just like pi. We say pi is 3.141 blah 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 blah. E is this number too, this irrational number, and it's a rational number of growth. If I was to continually grow something at a particular interest rate, and the time gets bigger and bigger and bigger, I would get to this number 2.718, and that is E. And E is used a lot in growth functions and monetary systems. It's used a lot in calculus. It's used a lot. It occurs naturally. It occurs in nature in terms of like spiral designs and things of that nature. And they call it the natural base exponential function. And it's a natural base exponential function, meaning your base is e. So it's e to the x. This irrational number, this 2.71828 blah 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 blah, is used a lot, and it acts just like a regular exponential curve, but it does have some unique properties that you'll figure out in calculus and pre-calc. But it is calculated the same way, and again, it's used a lot in money, and they call it compound interest. In this case with E, it's compounded continuously. I don't like that they don't talk about other compounding first. So when we do the equation using E for money, it's a function, A of t, where t equals time, is equal to the principal, which is the money that you start out with, times E raised to the R times t. So P is, they call it your principal. And that's the money you start out with. I'll say initial. Your initial money. R, that's your interest rate. And T, that's your time. And usually time is measured, in this case, in years. And if you wanted to do it in months, you would just have it some fraction out of 12. Okay. So how much will the account after 4 years of high school? So 5th grade, and it's deposited $300, $3,000 to the account. It pays 5% interest compounded continuously. How much will you have in the account when you enter high school 4 years later? All right, so 4 years later, and then 4 years after that, it's going to be 8 years. So A of t equals p times e to the rt. In this case, p is 3,000. That's the initial money we started with, times e. R is going to be 5% in decimal form, so 0.05. And then t is going to be 8 years. So it's going to be e to the 0.05 times 8. And that tells me how much money that this person would have in 8 years at 5% interest. There is a e on your calculator. At least every calculator should have a e. And guess what? This one does not. So I'm going to use the yep, it doesn't have it. So you are definitely going to need a graphing calculator to calculate. E cannot use a scientific calculator. So get a graphing calculator like so. Clear all of that stuff. And it was 3,000 times, I'll put in parentheses. I'm a parentheses nut, so don't judge me. Times, here's e right here. E to the, it was 0.05 times 8. So that gives me 0.4. And that will give me some number. And it looks like I will have $4,475.47 after 8 years. Okay. Alright guys, that is this section. I hope you have a great rest of your day.